Last time we gave the definition of a subspace. We said that a subspace is a non-empty subset of a vector space that satisfies two conditions, that it's closed under scalar multiplication and it's closed under vector addition. We said that a subspace inherits all other vector space properties due to S being a subset of the vector space. And we can think of S as a vector space inside another vector space, the bigger vector space being V. Let's look at some examples and some non-examples. Let's start with the vector space R2. Now, this vector space, in set notation, you can think of it as all the vectors x sub 1, x sub 2, where x sub 1, x sub 2 belong to the real numbers. And if I don't specify what the scalar multiplication and the vector addition are, then you assume that it's just the normal scalar multiplication and vector addition that you're familiar with. So x plus y is x1, x2 plus y1, y2, which is x1 plus y1, x2 plus y2. And then the scalar multiplication, alpha times x, is alpha x1, alpha x2, just like you're familiar with. Now we know that this is a vector space. We proved it a few videos ago. But let's say we have this subset of V, where S is equal to all the vectors in V that satisfy this condition, where x sub 1 is equal to 5 times x sub 2. I want to know, is this a subspace of our vector space V? So there's a few things we need to check. First off, we need to see if this subset is actually a subset. Are we getting vectors from V? Is it non-empty? And then we need to check if it's closed under the scalar multiplication and vector addition. So obviously this is a subset of V, because look, the vectors are in R2. This doesn't change that these vectors are in, like these entries are in R. It's just x1 is equal to 5x2. So examples of things that could be in this subset are 5, 1, 10, 2, and so on. If I just plug in 1 for x2, I'll get 5. And yeah, you can see that they're in V. And you can see that they're non-empty because this is a vector inside S, so it's non-empty. So let's write this down. S is a non-empty subset. So this is satisfied. That was one of the first things we had to check. Now we need to check that S is closed under vector addition and scalar multiplication. I'm going to actually write this set a little bit differently. I'm going to say that S is the set of all vectors 5b, b, such that b belongs to R. This is exactly the same thing, right? Because x1 is 5x2, so you just substitute 5x2 here. The only thing that we need to say is that x2, or here I say x2 is b, that's a real number. So it's the same subset. Cool. Now I want to check vector addition and scalar multiplication. So if x and y belong to S, does x plus y belong to S? Well, we need to come up with two vectors, x and y, in S, and see if we add them together if we're in S. So if we let x be 5b, b, that belongs to S, and we let y be 5c, c, where b and c are real numbers. Both of these vectors you can see belong to S, and x plus y is 5bb plus 5cc, which is 5b plus 5cb plus c. Now what we want to check is see if this vector is actually in the set. So can we write it in this form where we have 5 times a number and that number being here? And the answer is yes, because we can write it like this: 5 times b plus c, and then b plus c here. So b plus c is a real number, and then whatever that real number is, we're taking 5 times it. So that does belong to S. So S is closed under vector addition. The next thing we want to check is if alpha is a scalar, and since we don't specify the field of scalars, we assume it's the real numbers. If alpha is a real number and x belongs to S, does alpha times x belong to S? Well, let's see. If we let x be 5b, b, then alpha times x is alpha times 5b, alpha times b. But look, we can write this well, all of these are real numbers, and we know real numbers are commutative when it comes to multiplication. So this is equal to 5 times alpha b, and then alpha b here. So we have 5 alpha b, alpha b. And you can see this belongs to S because it's of this form here, where we have a real number and 5 times that real number. You can see real number, because this is a real number times a real number, and then 5 times it. So it does belong to S. So S is a subspace because it satisfies all the conditions we need to check for it to be a subspace. Let's look at another example. Let's say V is the set of 2 by 2 matrices. Again, I'm not specifying the vector addition and the scalar multiplication. You already know what it is. We know how to add matrices, and we know how to multiply a matrix by a scalar. And our subset is going to be the set of all matrices that take this form: A, B, negative B, C, where A, B, and C are real numbers. So what I want to know is S a subspace of V? Okay, so the first thing I need to check is S a non-empty subset of V? The answer is yes. If I put the zero vector, if I write the zero vector like this, well, does that belong to S? The answer is yes, because you have 0, 0, negative of 0 would go here, so that would just be 0 and 0. So that works. So it is a non-empty subset, but we also, let's check to see if everything that belongs in S would belong into the vector space V. And you can see if these are real numbers, they satisfy our 2 by 2, which is the set of all matrices A, B, C, D, where A, B, C, D are real numbers. So yes, it is a subset. Now we need to check, is S closed under vector addition? So if X and Y belong to S, is the sum X plus Y in S? Well, let's define X and Y. We need to come up with two 2 by 2 matrices that belong to S. They need to have this form. So we can let X be A, B, negative B, C, just like what we see here. And let's let Y be D, E, negative E, F. And we're assuming A, B, C, D, E, F belong to the real numbers. So you can see that these two vectors belong to your subset S. And if we add X and Y together, we'll get A plus D, B plus E, negative B, minus E and C plus F, which you can write as A plus D, B plus E, negative B plus E, C plus F. And now we have this is a real number, this is a real number, this one's the negative of what we have here, and this is a real number. So you can see that it belongs to S. The only entries that depend on each other are these, just like what we have for the definition of S. Our last step is to see if alpha is a scalar and x belongs to S, does alpha times x belong to S? Okay, so we're going to let x be A, B, negative B, C. Alpha times x is alpha A, alpha B, alpha times negative B, alpha C, which is alpha A, alpha B. We can move this negative in the front. And you can see this takes the form of elements in your subset S. So this belongs to S. And now we've checked all the properties. So S is a subspace of the 2x2 matrices. Okay, now I'm going to define S a little bit differently. Here I'm going to stick with the same vector space, the 2x2 matrices. But here S is all the vectors that look like this. 1, I fix a 1 here, but these other entries can change. So I want to know, is S a subspace of V? So one thing we're going to check is to see if it's non-empty, and it is a subset. Well, obviously, anything that looks like this, these are real numbers, so they would belong to your vector space. And we have the vector 1, 0, 0, 0, that belongs to S. So it is non-empty and it is a subset. So we're good with that. Now we need to check if vector addition and scalar multiplication hold. So let's go with vector addition. So if x and y belong to S, does x plus y belong to S? Well, we need to define two vectors that are in S. The only thing is we have to fix this right here. These can be anything. So we can let x be 1a, b, c, and y be 1, d, e, f. Then x plus y is going to be 1 plus 1, a plus d, b plus e, and c plus f, which is 2, a plus d, b plus e, and c plus f. Now, does this belong to our subset? Let's look back at it. These can be anything. They don't depend on each other. But this has to be a 1. You can see that these don't depend on each other, but this is not a 1. So this does not belong to S. There's no reason to check if scalar multiplication holds because one of the properties doesn't hold, so we're done. So we can say S is not a subspace of V. Let's do another example. Let's say V is equal to all the polynomials of degree less than n. So P sub n. And here I've written v in set notation. So all the polynomials p that when you evaluate it at x, it looks like this. And these AIs are in the real numbers. And now I'm going to take a subset of v. I want all the polynomials in this set such that when you evaluate them at 0, you get 0. So first off, let's try to figure out what S looks like. Like what kind of polynomials belong to S. So here's an example of a polynomial. 1 plus 2x minus 3x squared. This is a polynomial of degree 2. But if and in fact, let's call it p of x. But if I plug in 0, I get 1 plus 0 minus 0, so I get 1. So polynomials like this do not belong to S. I need to make sure that when I plug in 0, I get 0. So another way to describe S is the set of all polynomials in P sub n that are being the coefficients are multiplied by an x. So you could say a1x plus a2x squared all the way to a n minus 1 x to the n minus 1. And these AIs belong to the real numbers. So we want to see if this is a subspace of V. Okay, is it a non-empty subset? Well, the answer is yes. Obviously, we're saying there are polynomials in V, and it's non-empty because the 0 polynomial is in here. So if p of x is equal to 0, obviously p of 0 is equal to 0. So the polynomial 0 belongs to S. So it's non-empty and a subset of V. Now let's check if vector addition and scalar multiplication hold. So if x and y belong to S, does x plus y belong to S? So we're not going to pick specific polynomials. You want to check for any polynomials x and y in S and that this holds. In fact, let's call these polynomials p and q. I don't want to use that notation. So p and q belong to S. Does p plus q belong to S? Well, we're going to assume p and q belong to S. That means p of 0 is 0 and q of 0 is 0. To figure out if p plus q belongs, well, p plus q is a polynomial of degree n minus 1 or less. We need to evaluate it at 0. This is equal to p of 0 plus q of 0, and we know that this is equal to 0 plus 0, which is 0. So this sum, p plus q, it is a polynomial, and that when we evaluate at 0, we get 0. So that tells us that p plus q, this polynomial, actually belongs to S. The last thing we want to do is check and see if scalar multiplication, if S is closed under scalar multiplication. So if alpha is a scalar, p belongs to S, does alpha times p belong to S? Well, a scalar times a polynomial of degree n minus 1 or less is a polynomial of degree n minus 1 or less. The only other thing we need to check is that alpha times p, when we evaluate at 0, we get 0. Well, this is equal to alpha times p of 0, which is alpha times 0, and any real number times 0 is 0. So this tells us that alpha times p of 0 is 0, and that gives us that we are closed under scalar multiplication.